infinite sequences, as you remember, are just functions defined on the set of non-negative integers. So it's only reasonable to extend what we did with sequences to functions defined on, let's say, non-negative reals, or just on all reals. So we can define periodicity for functions. Let's do it. Let U be a function from R to a set S, or from R plus to a set S. So it's either defined on the whole real axis or it's defined on a half axis. R plus is the set of all non-negative reals. Let's define periodicity. A positive real D is said to be a period of U if every X satisfies U of X is U of X plus D. And of course, X is either in R in this case or in R plus in this case. So if every X in its domain Secondly, the function U is said to be periodic if it has a period. And thirdly, let D be a positive real. The function U is said to be D periodic if D is a period of U. So this is just a carbon copy of our definition of periodic sequences. Here are some classical examples. First of all, the functions sine and cosine from R to R are periodic, and actually they're 2 pi periodic. Since sine of x is sine of x plus 2 pi, and cosine of x is cosine of x plus 2 pi. And for another example, the function that sends each real number to x minus the floor of x. So what is this? This is the so-called fractional part of x. It's in a way, it's the part of x after the decimal point. But be careful with this, because for negative numbers, of course, the decimal point doesn't behave as you would expect. This function is 1 periodic. So this is pretty easy to see, because if you raise x by 1, then the floor of x also gets raised by 1, and x raised by 1, and the two ones cancel. And it is also easy to construct a function that's not periodic. I'm going to call it delta 0. It sends x to the truth value of x equals 0. In other words, 1 if x equals 0, and 0 if x is not 0. Is not periodic. Again, it's pretty easy to see. This is called the delta function. Simple but useful. And now we can take our old theorem about periodic sequences and basically just copy-paste it. So let U be a function from R or from R plus to some set. Then if A and B are 2 periods of U, then A plus B is a period of U. This literally holds. If A and B are 2 periods of U, and if we have A bigger than B, then A minus B is a period of U. Again, this is still true. This is also true. This is a bit, this gets broken a little bit, because what is the GCD of 2 real numbers? Well, but we can salvage it if we just restrict ourselves to integers. If A and B are 2 integers, or positive integers, that are periods of U, then GCD of AB is a period of U. Still true, for the same reason. And finally, P and Q are now, should be in the domain of U. UP, of course, becomes U of P. But more importantly, what does it mean that P congruent Q mod A when P and Q are not integers? Well, remember, Px congruent to Q mod A means that P minus Q is a multiple of A. And by multiple here we mean integer multiple. So we say that P minus Q is an integer multiple of A if P minus Q equals AC for some integer C, just as divisibility was defined. The proof of the theorem is exactly a copy of the proof of this theorem. Just subscripts become values, become arguments, I mean. Here is one more thing that's true. An aperiodic function, so another property of periodic functions, an aperiodic function is uniquely determined by its values on any given half-open interval of length a. In other words, if two aperiodic functions agree on a half-open interval of length a, so it looks like b plus a, I'm gonna have it open from the right and closed on the left, so including b, excluding b plus a. If two aperiodic functions agree on such an interval, then they agree everywhere. So they're equal. Let us restate this as a proposition. So proposition, let a be r or r plus, again, or we can have the half axis or the whole axis. Let u and v from a to s be, let's just say, let u and v be two periodic a, so, sorry, let a in, so let a be a positive real, let b be in the domain, let u and v be two functions in a that are aperiodic. If u and v agree on this interval, so by this we mean if we have u of x equals v of x for each x in this interval, then u is v. And the proof sketch, if you see a periodic function on an interval, so if you have an aperiodic function and you know what it does on this interval, you also know what it does everywhere else, because you just paste its plot on this interval, you just copy paste it over and over, you plaster the whole plane with it. So for the formal proof, see the notes. And I'm just going to show one little application of this proposition. Some of you have already discovered it. So as an application of this proposition, let us give a new solution to an old homework 0 problem. Recall this problem. Let x be, so prove that every positive integer n and every x real number satisfy this sum is this here. So alternative solution, I mean alternative to the ones that I gave in the notes. Define the two functions u and v from r to r by u of x is going to be the left-hand side minus the right-hand side. V of x is just going to be 0. We have to prove that this is an equality. In other words, we have to prove that this difference is 0. In other words, we have to prove that u equals v. Or also I should say fix n. So how do we prove that u equals v? According to this proposition, we could do it by finding a period and proving that they agree on a certain interval. Well, let's do it. Let a be in 1 over n. Then we claim that the function u is aperiodic. The function v is aperiodic. And finally, u and v agree on a certain interval of this form. And actually for b is 0. So I pick b equals 0. So I have to show that they agree on the interval between 0 and a. Once these claims are proved, the proposition above will immediately yield u equals v, and thus the problem will be solved again. How do we prove the claims? Well, the second, let me number them. Claim 2 is trivial. The function v is everywhere 0. Of course, it's periodic, not just aperiodic. It's anything periodic. To prove claim 1, we need to check that u of x is u of x plus a for each x in R. But how do we do this? U of x plus a is 1 over n. So let's do this here. Let's plug x plus 1 over n here. So x becomes x plus 1 over x, and this is also x plus 1 over n. Let's simplify. 1 over n plus k over n adds together to k plus 1 over n. And this here multiplies to nx plus 1. In the sum, we have this k plus 1, we rename it as k. So we substitute k for k plus 1. As a consequence, we get the same sum, but it goes from 1 to n, not from 0 to n minus 1. This is just the floor of nx plus 1. Because if you're adding an integer, you can pull this integer out of the floor. In our case, we're pulling the 1 out of the floor. Now let's look again at the sum. It goes from 1 to n. We wanted to go from 0 to n minus 1, so let's tweak it. First of all, we extend it to go from 0 to n, and then we subtract this new addend back. So let's repeat it here. X plus 0 over n, of course, is just 0. And now we split off this new addend for case n. So we let it go to n minus 1, and then we put that last addend separately. Okay, n over n is 1, of course. Floor of x plus 1 is floor of x plus 1, by the same reason as here. We're adding an integer. And now quite a bunch of things cancel. This floor cancels this floor, this one cancels this one. And here's what remains. But that's just u of x. So u of x plus a equals u of x. And that's the periodicity we want. Finally, let's prove claim 3. We need to show that the functions u and v agree on 0a. In other words, we need to show that u of x is v of x for each x in 0a. But you can easily convince yourself, do it, that, and that's also in the notes, of course. For each x between 0 and a, we have u of x. This is the formula that we've used to define u of x. And now I claim that this is 0 and this is 0. And so this is 0, and that's the same as v of x. So claim 3 is proved as well, and we're done. So it's an interesting indirect way of attacking this problem. Instead of computing the left and the right-hand side, we look at them as functions of x. We prove that they're periodic with period a, so 1 over n. We prove that they agree on this interval between 0 and a. And then, because of the periodicity, we conclude that they're equal. It makes for a maybe longer, but also a nicer and easier to think of proofs than we did on the notes. So periodicity can be useful even if you don't see it right away. That's, I think, the moral here.